Hey everybody, this is my lecture in Chapter 15, Structural Identification 2, Nuclear Magnetic Resonance Spectroscopy, which is shorthanded into just NMR. Just to make things short, NMR spectroscopy is the most useful spectroscopy we have to identify the structures of molecules. As we'll see throughout this chapter, there's many versions of it, and again, there's one great version of it that is used in hospitals, and we call those MRIs, which is magnetic resonance imaging. And so that came from our understanding of how molecules work in NMRs, and so you'll see that through here. I'm going to read the introduction to Chapter 15 because it does give a really good explanation for the value of doing this. So throughout history, nature has been a prolific source of medicines and important chemical products. 4,000 years ago, Sumerians recorded the pain-relieving properties of the willow tree, now known to contain salicylic acid as the active ingredient. Ephedrine, a component of the Chinese shrub ephedra, has been used for thousands of years in traditional Chinese medicine to treat asthma, hay fever, and bronchitis. Foxglove, a plant native to Western Europe, was used for centuries as a treatment for dropsy, or edema, the buildup of fluids in the lungs caused by heart failure. In the 18th century, it was discovered to contain the compounds digitoxin and digoxin, known as cardiac glycosides, for their ability to cause stronger heart contractions. As a result of their use in traditional medicines, a variety of plants, fungi, and marine organisms are mined as sources of medicinally important compounds. In addition to being medicines themselves, these isolated natural products often serve as lead compounds for further research and the development of clinically useful and safe medicines. Now I'm going to stop there and explain why I'm reading this to you. And it's that when you hear people say they're taking holistic medicines or things like that, there is a possibility that those medications are working. This goes on in the intro to say 70% of new medications in the past 25 years are derived from natural products. So getting holistic medications is potentially, valuable to the health of humanity and yourself. But keep in mind that for hundreds of years, chemists have been isolating these chemicals, purifying them, and using them pharmacologically to figure out what they do, if anything, and how they work, if they do, and then to synthesize them or synthesize modified forms of them, derivatives of them that have improved efficacy, essentially. So I just want to point that out as, in my opinion, if we hadn't figured out what's working with certain holistic medications in the past, I don't think we'd be where we are today. But also I think that for the most part, you have to consider that if it hasn't been discovered yet, like what's going on, it's probably bogus. Why do people eat shark fins and things like that in certain places of the world? I don't know. Or other gross things. There's no evidence that indicates there is a positive benefit other than just word of mouth. It's been long enough where things like this would have been studied, just like in these cases. Here, the salicylic acid from the willow tree, the ephedrine from the ephedra plant, and so on. Those were given as basically holistic medications. We later found out what they are, how they work, and then we made improvements upon them. So that's the process of chemistry, really. All right, so let me read here. Research is then done to modify the compound to eliminate the unwanted properties while maintaining the useful medicinal properties. Once a natural product is determined to have a desired activity, any further research on it requires elucidation of its structure. This is where infrared spectroscopy, mass spectrometry, and nuclear magnetic resonance spectroscopy come into play. As we study the principles and application of NMR, a case study of the isolation of Kerasin A, a potential cancer treatment, is presented. So this is in section 1, nuclear magnetic resonance and overview. NMR is another form of spectroscopy like IR. NMR uses energy in the radio frequency region of the electromagnetic spectrum. This energy corresponds to the energy required to flip nuclear spin. All right, so the nucleus of an atom is, if you're thinking of a hydrogen atom for simplicity, it has one proton, and you can think of it as a particle that spins. It has a charge, it spins, just like we talked about electrons spinning, either up or down spin. We can say the proton has up or down spin as well. All right, so the energy that we're going to irradiate these molecules with corresponds to the energy required to flip the nucleus, essentially. Under conditions in which an NMR spectrum is recorded, this energy depends on the environment of the nucleus. Being at the long wavelength and low frequency end of the electromagnetic spectrum, radio waves are very low energy. As we can see here, low frequency, low energy, because E equals h nu, where h is Planck's constant, 6.626 times 10 to the negative 34 joule seconds. And then the nu here, Greek letter nu, is the frequency in hertz. All right, so the lower the frequency, the lower the energy. The higher the frequency, the higher the energy. But you also should remember that wavelength and frequency are inversely proportional. So the speed of light is equal to the product of lambda nu, where this is the wavelength. In a vacuum, the speed of light doesn't change. So if you were to increase the frequency, the wavelength would have to decrease, and vice versa. Either way, though, in the end, this is all low energy stuff, so radio waves cause no problem for humans. You're surrounded by radio waves all the time from radio stations. Your cell phone is actually emitting radio waves. The sun is emitting radio waves, and so on. It's just all around us. You're not going to get a brain tumor by holding a phone to your head, because there's way more radio waves floating around and interacting with you than the phone would give off. Your whole life you're being bombarded with them, so you don't need to worry about it. As we discussed in the infrared and mass spec chapter, different energies, different types of electromagnetic radiation interact differently with molecules, because they have to have the requisite energy to cause an electron in a highest occupied molecular orbital, the HOMO, to excite into the lowest unoccupied molecular orbital, the LUMO. All right, and if you don't have the right energy, then nothing happens. The electromagnetic radiation passes through a sample of molecules like that. The energy required to flip the nuclear spin and cause an NMR signal is the lowest of all energies used. You can see that X-rays cause ionization, UV vis is electron excitation, infrared radiation is molecular vibrations, and microwaves, at least from 1 millimeter to a meter in length, cause bond rotations, and microwaves from 1 meter to 100. I have a feeling this is supposed to be radio waves, yes, which is what it is in the book. The radio waves from a meter to 100 kilometers cause flipping nuclear spins. All right, NMR spectroscopy gives us information on the chemical environment of every hydrogen in a given molecule. An NMR spectrum is a plot, like you see down below, showing the frequencies at which electromagnetic radiation is absorbed. On the spectrum, each spike in the spectrum is a signal representing where electromagnetic radiation was absorbed. Rather than something that's being emitted, this is an absorption spectrum. All right, so there are 4 important parts of the NMR signal, which one of them looks like this. You see that this signal consists of 3 peaks, 1 big peak and 2 smaller peaks. The middle peak is going to be used to determine the chemical shift. The Chemical shift gives the location of the hydrogen relative to other functional groups in the molecule. In this case, it is next to a carbonyl, and we see the peak is at 2.4 ppm, or parts per million. I know that doesn't sound like a frequency, but that's what we call it. Don't worry about it right now. All right, so the signal indicates the presence of a hydrogen, and this one has a chemical shift of 2.4 ppm. Different functional groups can change the location of the peak. So you could have the same peak of this, what we call a triplet, with two smaller peaks and one big one in the middle. It could be at 2.4, 2.5, 1.8, 3.7, whatever. Depends on the rest of the molecule in a sense. We're going to integrate the peaks in an entire spectrum. So you see in green here, the integration tells how many hydrogens are in that particular signal. It has to be relative to something you do know though. So right here, that you see that the integration has two hydrogens. Yes, and we're giving you a structure there that has two hydrogens at that location, but without having some sort of knowledge of the molecule, you wouldn't necessarily know that. So you might integrate every peak and make the one that has the smallest area a value of 1, and then you could see how much each of the other peaks have, how many hydrogens each of the other peaks have. Then the last thing to consider is splitting. Splitting tells how many neighboring hydrogens there are to the ones in question here at this signal. So in this structure, you see there's two hydrogens here that are neighbors to the two that are highlighted in orange. And it always works out that the number of neighboring hydrogens, you add 1 to it, and that'll give you the number of peaks you see in your signal. So this is a triplet with the 3 peaks, and therefore it must have 2 neighbors. I also should point out here that each signal doesn't necessitate that this is one group by itself. It could be a molecule that is symmetrical, and the environment of 2 different groups of hydrogens could be the same and give you the same exact peak. So for example, the picture we see here is incomplete in a sense. Oops. But if I were to draw it like this, there's 2 hydrogens here, 2 hydrogens there, and I'll just finish off the other sides by saying these are CH3s. The pair of hydrogens here are the same as the pair of hydrogens there because the molecule is symmetrical. And I could also say that the 2 methyl groups here and there are also the same. So this one would only have 2 peaks. If we were to draw or predict an NMR spectrum for that molecule, you might see these have 2 neighbors, so they would be a triplet. And the ones circled in yellow would have 3 neighbors, so they'll actually be a quartet. And so you'll see a quartet, you'll see a triplet, and they generally look like that. The actual values of the chemical shift, again, still depends on the rest of the structure of the molecule. We do have the carbonyl there, which changes things. So we'll get into the details of that going forward, but you only have 2 peaks in this molecule as a result of the symmetry of it, even though there's technically 4 groups of hydrogens. All right, we can see from table 15.2 here, we have the types of protons or hydrogens and their approximate chemical shift in ppms. So we see a terminal alkyl group or methyl group has an approximate shift of 0.9 ppms. So that can be changed, again, based on the rest of the molecule through electronegativity differences, induction, hyperconjugation, things like that. We see the next one down, alkane, again, but this is a methylene group, CH2, within a, let's say a saturated hydrocarbon, you have a shift of 1.3. For a methine, you have now this tertiary carbon, and it's got a shift of 1.4. The methyl ketone, 2.1. So again, it's a methyl group, but now we have the ketone next, or the carbonyl next to it. So that's what we call deshielding. It takes away electron density around the hydrogens, so their frequency is going to increase. The acetylenic hydrogen there on the sp hybridized carbon is 2.5. So again, we have this group there deshielding that hydrogen, moving it further to the left at 2.5. And then at the bottom we have the methylene group hydrogens attached to the halogen. And so that goes between 3 and 4 ppms, depending on what the halogen is. It does also put oxygen there. Those are going to be deshielded due to electronegativity differences. So this is a continuation of table 15.2. We see the vinylic hydrogens have 5 to 6, allylic hydrogens 1.7. So what you can see here is that this carbon is sp2 hybridized, that carbon is sp3 hybridized. If we go back to, I'm not going to go back to the previous slide, but if we went to acetylene again, this was sp hybridized, and its shift was 2.5. And so then you have the aromatic one, like on a benzene ring, is 7.2. You're going to see a lot of that. A benzylic one is 2.3. Aldehydes are 9 to 10. Carboxylic acids, at least the acidic hydrogen of that, is 10 to 12. And then alcohols are variable, it says, from like 2 to 5. But sometimes you won't see them because they'll also be broadened, and sometimes they're broadened to the point where they're flat. If they're not broadened out, they tend to be a single peak, and they can be anywhere. Again, it just depends on the rest of the molecule. Right, a phenol one is from 4 to 7, and finally the hydrogens on a nitrogen in amines range from 1.5 to 4. All right, so the integration of each signal gives the relative number of hydrogens giving that signal compared to others in the spectra, as I mentioned earlier. If I go back to this molecule here with these two hydrogens and then the CH3s and these two hydrogen and the CH3s, the peaks, you have the quartet and the triplet. If we were to integrate those, to show that here, it would look something like this. And the quartet would have 4 total hydrogens, while the triplet would have 6. So you might see a 2 to 3 ratio, or really you might see a 1 to 1.5, because again, you probably are going to make this the one with the smaller value 1 just as a starting point. So if you saw 1 and 1.5, you would know that's really 2 to 3 or 4 to 6. But it does, again, we wouldn't necessarily know there's symmetry without some other information. So like if you knew the chemical formula was C, in this case 5H 10, it looks like, and then O, C5H10O, then you would be able to figure out its structure from these two peaks. The quartet and the triplet will be pretty obvious. The splitting of a signal is related to how many hydrogen neighbors it has. With n neighbors, the peak will split into n plus 1 signals, as I mentioned earlier. All right, so we have an NMR spectrum here of a molecule with a chemical formula of C4H9Cl. All right, you can see that in this spectrum we have 4 major peaks. The one on the far left has an integration of 2. Then the second from the left has an integration of 2. Second from the right, integration of 2, and then the far right is an integration of 3. Those add up to 9, which we see in the molecular formula. So you know, based on that this has no symmetry. Now you're coming into this having a sense of its chemical formula. Just so you know, like without the chemical formula, all we know is there's 4 different types of hydrogens. and we could know the splitting and stuff like that, but otherwise you wouldn't have enough information just from the NMR. So anyways, we'll first look at the index of hydrogen deficiency to figure out if there's any double bonds, and that will be 2 times the number of carbons minus the number of hydrogens minus the number of halogens plus the number of nitrogens, and then plus 2, and then all of this divided by 2. For this molecule, we get 2 times 4 minus 9 minus 1 plus 0 plus 2 divided by 2. So you get 8 minus 9 minus 1 plus 2 over 2. So you get negative 1 minus 1 plus 2 over 2 is negative 2 plus 2 over 2, or 0 over 2, which is 0. So there are no double bonds in this molecule. All right. If you think about it, butane here is C4H10. Let me draw the hydrogens out. This is the saturated hydrocarbon, butane, and you can count the hydrogens, you'll see 10. If I replace one of the hydrogens with the chlorine, you see that it's still saturated in the sense that there are no double bonds, but we've lost a hydrogen. So it goes down to 9, and so the chlorine is replacing a hydrogen there. All right, so I don't know where that chlorine is, but let's look at the structure, or the spectrum of it. So we see a triplet at 3.5 ppms. We see a quintet here. And then we see a sextet at 1.5-ish ppms, and then again a triplet at about 0.9 ppms. All right, so we have a triplet, which looks like that. That means there's the number of neighbors will be 2, and then we've got 2 of those. Okay. Then we've got a quintet. And the number of neighbors for those will be 4. Then we've got a sextet, which will look like that usually. And the number of neighbors there will be 5. So you see the number of neighbors add up to 11, which is more than 9, but what that indicates is, like, if we were to look at this hydrogen here, the neighboring ones will be these 3 and these 2. So if we looked at that hydrogen, it has 5 neighbors, and so it would be a sextet. The fact is that these ones that I've circled in red are going to be exactly the same, because the shape and orientation of the molecule relative to those 2 is going to be identical. So there's no difference between those, because the molecule is achiral. Those hydrogens are achiral. The carbon they're bonded to is achiral. Obviously, we're ignoring the chlorine for now. All right. So we have this issue. So we have one hydrogen. Well, actually, if you look at it, it has an integration of 2. So that probably does indicate that we have 2 hydrogens there, 2 hydrogens there, and let's say the sextet is for this hydrogen, and then there's 1, 2, and 3. So the one I've circled, or the 2 I've circled, would give you an integration of 2 and a splitting pattern of a sextet. Now we have a quintet, with 4 neighbors essentially. And you see the quintet has an integration of 2 as well. All right, so again, we're going to have 2 hydrogens, and then they're going to have only 4 neighbors. So let's make this like an R, and I'll put an R here. All right, and so we can see that these two hydrogens have 1, 2, 3, 4 neighbors, and therefore will be a quintet. And then we've got two triplets, one of which integrates to 2 and another one that integrates to 3. Well, if we have one that's integrating to 3 and it's a triplet, that means it has 2 neighbors. And so there's the integration of 3, and here's the 2 neighbors, so that would be a triplet right there. All right, and again, integration is going to be equal to 3. We see that's probably this. Integration of 3, it's a triplet. All right, then we have the other triplet, which integrates to 2. So let me get a good color here. All right, so we've got carbon with 1 and 2, and then something else. And then, sorry for my bad drawing here, but we have that. So now when we're looking at it, these two will be a triplet because of those two, and they're going to integrate to 2. So putting this all together, we have like 4 pieces of the puzzle here, and there's only 4 carbons, right? So putting the puzzle pieces together, I think, and I didn't know that when I was up here, I basically drawn the correct structure. It was just a guess, but this is the molecule, C4H10Cl, or not C4H10, C4H9. Let me get that out of the way. Cl. All right, so again, if we look at these 3 hydrogens here, these will be a triplet. They'll integrate to 2. These 2 hydrogens will be a sextet, and they will integrate to 2. Those 2 will be, if you look at the neighbors, we've got those 2 plus these 2, so they have 4. So these will be a quintet, and they'll integrate to 2. And then finally, I'll just circle them in yellow now. We have only the 2 neighbors that are circled in white, and so that would be a triplet, and they're integrating to 2. The next thing to consider is that the chlorine there is next to the carbon that has the yellow hydrogens, the triplet at 2, or triplet with an integration of 2, and triplet there. And you can see that the chlorine is actually de-shielded the peak. It's made it go further downfield, essentially. And so that's what we see. And then we could look further. The quintet is closer to the halogen. You see that one's the next furthest to the left. Then the sextet is next. And finally, the methyl group at the far end is furthest away from the chlorine, and hence it's all the way at the right there. So that was a simple NMR for a simple molecule, and it used what we call hydrogen 1 spectroscopy. Hydrogen atoms, the nuclei of them, do flip in radio signals, and so we call it proton NMR or just HNMR. But it's not the only one you use. Obviously, as the organic chemist, that's the easiest thing for us to do because almost every organic molecule has hydrogens in them. But sometimes we want to look at other things. And so there's carbon 13, there's fluorine 19, phosphorus 31, carbon 12, no. Okay, so these are the most commonly used spectroscopies: hydrogen, carbon, fluorine, and phosphorus. You see the number of protons are 1, 12, 9, and 15. The number of neutrons, 0, 13, 10, and 16. And the key there is that the sum of these is going to be an odd number. Whereas for carbon-12, it's an even number. And so the result of that is that everything kind of cancels out for carbon-12, so it doesn't work. And the same would be true for carbon-14. Okay, so the nuclei of atoms have two spin states. They're either up spin or down spin. They could be, therefore, up with a half or down with a minus 1/2 spin state, just like electrons were able to do that. We don't need to worry about the half, what that means. It does have significance, but it's kind of irrelevant for nuclear magnetic resonance spectroscopy. When you take a sample of atoms and they're absent a magnetic field, the atoms just spin up or down, clockwise or counterclockwise, really, and the atoms are orientated just randomly in space. So you get a whole bunch of randomly orientated magnetic fields as a result of the nuclear spin. All right, but when you place them in a magnetic field, they will align either with the magnetic field or against the magnetic field. But they're going to be parallel to it. You see, the BO there represents the magnetic field, the strength of it. The stronger the magnetic field, the more likely they will align with it and everything. But you put a sample inside of a giant magnet, and everything will align with it because the spinning charge creates a magnetic field, and they're going to go to the lowest energy system, which is aligning with or against the field. When these particles, atoms or molecules, align with or against the magnetic field, they actually have different energies, and you can see the obvious cases with the magnetic field has a lower energy, and against the magnetic field has a higher energy, and there's a difference of energy in there. And you can see delta E equals h nu, and again, that frequency is going to correlate to a radio signal, the amount of energy required to cause this flipping. As we were wont to do throughout this whole 2 semesters of organic chemistry, we like to do energy coordinate diagrams, and you see energies, then the y-axis increasing going up. We have the reaction coordinate is the x-axis going to the right, being time, I guess. And then you have alpha spin and beta spin. The alpha spin is the state that has this spinning with the magnetic field, and the beta spin is when it's spinning against the magnetic field. You see there's a slight delta E, and again, the difference in energy there is equal to the amount of energy required to cause an alpha spin to flip to a higher energy beta spin. And in this picture, we can see the same kind of thing, but you'll notice that the delta E between the alpha and the beta changes based on the strength of the magnetic field. The stronger the magnetic field, the more likely it is for all of the molecules to be in the alpha state rather than the beta state. And so the gap gets larger, and you need more and more energy to do that. So in other words, you get a better resolution of the 2 spin states with a better magnetic field. So really high-end NMRs will have humongous magnetic fields. Like the one that I used in graduate school was pretty large, and we couldn't have our cell phones or credit cards on our body near it within, let's say, 25 feet of it, because the magnetic field goes outside of the instrument and can damage electronics. So but the bigger the energy gap, the better resolution we get, meaning our peaks look better. The one in our laboratory is a very small NMR machine. The frequency or the magnetic field is very small, so you're not getting good separation of peaks. So you'll see when we finally do spectroscopy with it from the labs that they look bad, especially compared to what you might see in the pictures in this chapter. The delta E between the alpha and the beta spin states is proportional to the strength of the magnet in the instrument, and resonance will refer to the frequency that causes a nucleus to flip. It's not related to movement of electrons in resonance like we talked about before, but in a sense you're resonating back and forth between the alpha spin and the beta spin and so on and so forth. You might have heard of resonance frequency, like when a singer makes a glass break from singing a very high-pitched note. That's the resonance frequency of the vibrational frequencies of the glass. If you match that, turns out the glass will vibrate back and forth and get stronger and stronger and bigger, and eventually it breaks. In the same kind of sense, if you match the frequency in your magnetic field with the radio waves going in, they will align with or against, and it will go back and forth and release energy, is ultimately what we're going to get out of this. The atoms and molecules that we place into the NMRs will spin, as we mentioned, and as they spin, they will actually precess, just like the Earth precesses. I think every 13,000 years or so, the Earth precesses. It wobbles in a sense. So if you spin a top, it doesn't perfectly spin. It'll eventually start to wobble, and then it slows down and whatever. Well, the atoms here and molecules will precess or wobble, and they won't slow down necessarily. But the frequency of the precession, how often it goes around, this loop, essentially, that's its resonance frequency. And if you put in a radio frequency that matches that precessional frequency, you can get the spin of the nucleus to flip. We have right here this spinning counterclockwise. You put into that radio waves that match the frequency of it, and it flips to now just being clockwise. You can see here in this picture, again, this is a photograph from your book, how the NMR actually works. You place a tube, which we just call an NMR tube usually, inside of the NMR instrument. That will end up going in, and there's a mechanism that will cause it to spin around, and so you'll be getting a homogeneous mixture inside. And the way the instrument detector works, it's never seeing the same thing, so you're not having any imperfections as a result of that. But it's placed around this superconducting magnet. Now that would be usually like the way it's shown, this would be a cheap NMR like the one we have, between two magnets. But you can only make magnets like that so strong, or the things would be massive. But really, really high-end NMRs will use a superconducting coil of copper that surrounds the sample. So instead of that, it might look more like this, coiling around the whole thing. I know that's not a good drawing, but it is what it is. I can only do so much on this picture. And that way, they can create much larger magnetic fields. And I've seen these NMR machines, instruments that are, a diameter of 8 feet, something like that. And, they're also tall, like 10 feet tall, something like that. They can be huge, and you got to climb up a ladder to get into them and put your sample in. But you see there's a radio wave input, a RF transmitter, and there's a radio wave output, a detector there, and so you have something to put radio waves in, you have something to read what comes out through the sample, as like, it's kind of like this is, let me color code this. Give me a second while I get the color. We have these in the back from the transmitter, and now I need to find the next right color. All right, and then the detector is in the front. All right. But then we've also got the magnetic field going from one direction or the other, essentially. And so the transmitter will shoot radio waves into the sample. The detector reads what happens as a result of it as they're aligning with or against the magnetic field. All right, that sends a signal to a computer, and then some high-end mathematical transformations called Fourier transforms convert that to the signals we see. So the picture here is showing an NMR and explaining that, let's say peak A, which is at a ppm of 1, right here, is the nucleus that feels the weakest magnetic field. It's easier to flip, so delta E is small. So the frequency at which it processes and then flips is small. Again, we're saying it's about 1.1 ppm there. B is slightly upfield at a chemical shift of about 4. And the nucleus there of the atoms responsible for that feel an intermediate magnetic field, harder to flip than those of A. So delta E is a little larger, hence why it's to the left. All right, and so then we look at C, and that one has the highest ppm, and it says there the nucleus that feels the strongest magnetic field is hardest to flip, delta E is largest. In this molecule, whatever this is, if you had all these hydrogens and they were all the same, you would get just one peak. Let's say it was just looked like that, one, whatever. It might look like just this if every hydrogen was exactly the same. So in a molecule like CH4, 4 hydrogens, you'd get one peak. All right. In a molecule like ethane, you'd get also one peak. The shifting may be technically slightly different, but either way, the appearance of it would be the same. We could take hydrogen, and it would look like that. But in other molecules, let's just say like in propane, there are inductive effects, there are hyperconjugation effects, resonance effects, that can change the environment surrounding the hydrogens, and so they actually will be different. You know, if we have the hydrogen here spinning and that hydrogen there spinning and that hydrogen there spinning, their environments are the same because this bond is allowed to rotate. And likewise, these two will be the same because both of the bonds surrounding it are allowed to rotate. And then, you know, because this side is ultimately the same as that side, these two end up being the same. But they're different than these, all right? Because the environment surrounding these are not the same as the environment surrounding those. Right? We only have one carbon next to this carbon next to that hydrogen. Whereas if we go, and so let me count this out for you. If we start here at the hydrogen I've labeled yellow, and we go 1 and 2 bonds away, we get 1 carbon. And there's a carbon right there. If we start in the middle, let's say this hydrogen here that I've now got green, going 1 and 2 bonds away, we get that carbon, but we also get this carbon over there. So the environment of the green hydrogen is different than the environment of the yellow hydrogen. But that set of 3 hydrogens is the same as this set of 3 hydrogens. So propane should have 2 different peaks. And then the splitting and all that, it's all, again, related to how the magnetic field works. Now when we look over here, in this picture we see 3 peaks, and we can see how they're split, and we don't have an integration there. But the key part here to learn is that each unique hydrogen atom in a molecule will experience slightly different magnetic fields. Slight differences in the magnetic field result in slightly different delta E values between alpha and beta. All right, so we look at the peak at about 1.1 ppm A. The nucleus or nuclei feels a weak magnetic field and are easy to flip. And then for B, they're further to the left at a ppm of about 4. The nuclei there feel an intermediate magnetic field and are harder to flip. Delta E is larger. And finally, for peak C, it's all, down at about 5 ppm. The nuclei there feel the strongest magnetic field and are hardest to flip. The difference in energy from the beta, or from alpha to beta, for each of these, they differ because their environments differ. And so you have a larger delta E going down to a small delta E, and so they show up at different places in the spectrum. Hydrogen in a molecule can be equivalent by one of two symmetry elements. Hydrogen atoms can be related by a plane of symmetry, or they can be related by rotation. If you look at the molecule here, it has one set of hydrogens. They get one signal because the molecule is symmetrical. I'll give you a better example, because really that is a cyclohexane and is three-dimensional, right? But we've got the axial and the equatorial hydrogens. You've got the two different chair conformations like that, and it's flipping back and forth between them. And so that one's maybe a little difficult to see, but if you can draw it flat and it's symmetrical, it's probably, or it can be symmetrical in 3 dimensions. But if we look at benzene, benzene is flat already. And I'm going to put the hydrogens in. You can see that it doesn't matter where I draw my lines, molecule's symmetrical through each of those lines. So all 6 of the hydrogens are the same. Again, we have that hydrogen, and we go 1 to 2 and 1 to 2. There's a carbon with a hydrogen, which goes down to a double bond to another carbon and a hydrogen over here to a carbon and a hydrogen, and they both end up going down to this carbon and that hydrogen. So there's no difference. The molecule's symmetrical. Hence you get one peak there. Now, again, you can have symmetry due to bond rotations. I already kind of discussed that in the previous slide, but this set of methyl groups will be the same because bonds can rotate. All 3 hydrogens will be the same on each of those. If we had, let's say this over there at that A was this acyl chloride, we'd still have the 3 hydrogens on the right, and those 3 would still be the same because this bond can rotate around. So let's call these hydrogens 1, 2, and 3. If you then rotate the AB bond there around, you might get an orientation that has these of 2, 3, and 1, and so on and so forth. You get others. Since it's spinning, the spinning of the bond is going to be faster than the frequency of the instrument, so it doesn't notice a difference. So it comes out as one peak. And then you've got the 2 over here, which will definitely be different because they're closer to the chlorine than the ones on the right. And there's 2 of them. Again, both of these bonds can rotate. And so both of those hydrogens are the same. And so this molecule would have only 2 peaks, whereas benzene would only have 1. Each unique set of hydrogen atoms gives its own signal in a proton NMR spectrum. All right, for the molecules shown, give the number of signals expected and the relative ratio of the signal integrations. All right, so what we're going to have here will be that these 3 will be the same. This carbon does not have a hydrogen, so there's no hydrogen there. This is going to have its own peak. We'll have a peak here, and we'll have a peak there. So you see there's blue, yellow, green, and black, 4 different signals. The integration there, just to remind you, these are CH3s because they're terminal carbons. So those will be 9. This is a methylene group, so this will integrate to 2. We have another methylene group here that'll integrate to 2. And then we have the hydroxyl hydrogen here, which will integrate to 1. Come on. There we go. All right. For this molecule, we're going to have these being the same. The green one now does have a hydrogen there. So we have CH3s. We've got a hydrogen here. And all those bonded to the benzene ring. So as far as different hydrogens here, the two hydrogens there will be the same, because again, this bond can rotate around. So all the stuff there will end up being the same towards both of those hydrogens. All right, we're going to have these two being the same and that one being by itself. It is not going to be the same as this hydrogen there. So this one's going to have multiple different peaks. This one's going to integrate to 1. Those will integrate to 2, 1, and 6. All right, nuclei in a molecule are surrounded by electrons that, as spinning charged particles, also create their own magnetic field. When the spinning electrons work against the external magnetic field, the nuclei will feel a smaller magnetic field, resulting in a smaller delta E between alpha and beta spin states and a lower resonance frequency. This is known as shielding of the nucleus. So again, to kind of reiterate this, a proton surrounded by electron density is shielded. The electrons are spinning. They're creating their own magnetic field, so they're kind of blocking the magnetic field that you're putting the molecule in. The induced field decreases the strength of the magnetic field felt by the nucleus, so this nucleus is shielded. All right, an isolated proton, though, is going to feel the magnetic field that you put it inside of only, and so it will be de-shielded. The position of the signals in the spectrum is referred to as the chemical shift and is expressed in units of parts per million. The chemical shift is a simplified way of telling how different the resonance frequency of a given nucleus is relative to the resonance frequency of a standard. TMS here stands for tetramethylsilane, and it has a chemical shift of 0. Tetramethylsilane is this. Since this molecule will end up being symmetrical, we can use it as a reference for everything else. You see the chemical shift is going to be equal to the shift from TMS in hertz divided by the spectrometer frequency in megahertz. All right. The NMR spectrometers come in a variety of frequencies ranging from 60 megahertz to a gigahertz, with the most common instruments being either 300 or 500 megahertz. Thus, the chemical shift of a set of protons is corrected for the strength of the magnet used. The computer does all that work for you. So the chemist will put a sample of TMS in the NMR, and depending on the strength of the NMR, its frequency that it can use, they'll find a shift in hertz and divide it by the frequency of the spectrometer and get a value. We're going to call that its chemical shift. Because this is not really 0, you can standardize and normalize the peak by making it 0. So you might get, let's say you have 0 ppm there and your TMS peak ends up being here. We can kind of just shift, well, it didn't work the way I was hoping, but we can kind of just shift the scale over to make the 0 ppm now underneath the TMS peak. And then everything else will still be relative to that, ultimately. In the NMR we usually are using the reference material of deuterated chloroform, which is CdCl3. All right, that is the solvent we use. to dissolve everything in. Because it has deuterium as the solvent, there's no hydrogens in there, so that one will not make any peaks. But we can still add things in there as reference points, like the NMR tube the machine comes with or is set with all the time has some TMS in it, and then we run our own spectrum and the shifts will be relative to that. So here we have the effects of electronegativity on chemical shift. All right, so sigma bonded electrons will shield nuclei from the external magnetic field, whereas a highly electronegative atom polarizing the sigma bond by withdrawing the electrons will de-shield the nucleus. That's through induction there. When nuclei are shielded or de-shielded to a different degree, they'll have different resonance frequencies and thus a different chemical shift. In older terminology, downfield is synonymous with de-shielded or higher values or to the left of the spectrum, whereas upfield is synonymous with shielded, lower chemical shift values, those to the right. All right, so you see in fluoromethane, we have the electronegativity values of the fluorine. For methanol, we have it for the oxygen, chloromethane for chlorine, bromomethane, bromine, iodomethane, iodine. Then you've got the carbons and silicons electronegativity values. You can see the effect they have on the chemical shift of the 3-methyl hydrogens. For ethane, it's at 0.9. That's like the standard. If there's a silicon here, well, that's from TMS. It's the standard, so it's going to be at 0. Because, again, TMS is a silicon with 4 of these methyl groups. So if you had another molecule with silicon bonded to methyl groups, then they wouldn't be any different. So that's why they're 0. And then you see the iodine followed by bromine, chlorine, and fluorine. So going down the periodic table, the electronegativity values go down or go up as the electronegativity values increase going up. And so that means the fluorine is pulling the electrons away from the carbon and the hydrogen there more than the iodine would. So they are de-shielded. They're not blocking the hydrogens as much as what you see in the hydrogens of the methane there. And I'll remind you that carbons are considered to be electron donating, so they're shielding the peaks. So we see we get 0.9 there. The iodine is de-shielding, so it goes from 0.9 to 2.2. Bromine even more de-shielding, 2.2 to 2.7. The chlorine de-shielding even more. The fluorine de-shielding the most. Obviously, we have a hydroxyl group right in there. The oxygen has an electronegativity of 3.44, so it's de-shielding even more than chlorine is. TMS is used as the standard in NMRs usually because the carbon-silicon bond is polarized in the direction of carbon, making it partially negative. The methyl groups are highly shielded from the external magnetic field, meaning it's going to be far to the right. All hydrogens attached to a carbon atom will be de-shielded compared to TMS. The spectra shows the terminology on the previous slide. Whereas de-shielded is to the left and shielded is to the right. Though chemical shifts can vary, a few functional groups' chemical shifts are worth mentioning and knowing. Aromatic hydrogens appear between 7 and 8, and they'll usually have a bunch of overlapping peaks and be kind of small usually. It'll be pretty obvious what they look like, and we'll see that in our labs because we used benzaldehyde. So you'll get a good look at what aromatic NMRs look like. They're significantly de-shielded compared to the corresponding alkyl hydrogens, from 0.9 to 7 to 8. Alkenyl hydrogens, ones bonded to an alkene, are slightly de-shielded or intermediate. They have an intermediate de-shielding. between 5 and 6, and then aldehyde protons will be between 9 and 10. They're the most deshielded. The reason for the deshielding is related to the magnetic field of the electrons working with the external magnetic field. So you have this is a benzene ring. The magnetic field that is opposite the external field is induced at the center of the ring, because you have the electrons spinning around above and below the benzene ring. But its magnetic field lines curve around, as we can see in the magenta arrows. Where the hydrogens are, the field is working with the external field, meaning they're actually going to be deshielded. Again, it goes from 0.9 to like 7 to 8. As a result, aromatic hydrogens are deshielded, which gives them a higher resonance frequency. Note that an alkyne with a second pi bond, it's like acetylene, is going to end up between an alkane and an alkene. So it's not quite as deshielded as an alkene would be. Right here we have the alkenes and aldehydes and why they're deshielded. You see at the top regions and the bottom regions for both of them, the magnetic field induced by the pi electrons works against the magnetic field. They're going down. Whereas the magnetic field is going up. Going down, going down, going up. All right. But when they've come around and now they're coming in that direction or this direction, they're going with the magnetic field. So in those regions, here and here as well, the magnetic field induced by the pi electrons reinforces the applied magnetic field, resulting in a deshielded set of hydrogens that appear at a higher chemical shift. Now, the explanation for why alkenes and aldehydes have vastly different shifting patterns when you're comparing them would be that, well, they're not the same. You have to consider that the carbonyl of an aldehyde looks like this, and there's going to be significant resonance contributions that looks like this. And so you see the carbon is completely deshielded by the oxygen in this resonance structure. And therefore, that's pulling electrons away from the hydrogen, deshielding it even more. Whereas in an alkene, you're not getting that. And yes, we're comparing these two. In the alkene, you don't get that deshielding effect. You also have a more electronegative oxygen versus the carbon. So through induction and through resonance, the hydrogen of the aldehyde is much more deshielded than those of alkenes. Again, I had to take a picture of my book, but this is representing like acetylene. So you can see this is kind of supposed to look like that. And for the acetylene, in the region at the top, you have the arrows going down again against the applied magnetic field of the NMR, and those are going to work against the applied magnetic field, effectively shielding the nucleus, making it easier to flip. Whereas going around over there, they're going with the magnetic field, which reinforces the applied one, obviously, and that's going to effectively de-shield the hydrogen. So anyways, since the hydrogen that I've circled is in a region that is going against the applied magnetic field, it is overall shielded relative to alkenes and aromatic groups and aldehydes. So their chemical shifts are much more upfield than the other ones we saw at about 2.5 ppm. The methyl hydrogens in propane appear at a chemical shift of 0.9 ppm, whereas the methyl hydrogens of propene appear on 2.5 ppm. Explain. All right, so in propane, there's nothing really to deshield the three hydrogens that are highlighted there. They're next to a carbon that is a methylene carbon that is also bonded to a methyl carbon at the far left end. So it's all just carbons and hydrogens. There's nothing deshielding there. Then you look at propene, and you have a chemical shift at 2.5 ppm. And the reason that would be is that the alkene is electron withdrawing right there, that alkene. So it deshields the allylic protons, the ones on, let me change the color here. The 3 hydrogens right there, those are the allylic protons. The alkene is electron withdrawing, so deshields them. The induced magnetic field from the pi electrons, as we saw 2 slides ago, reinforces the magnetic field near those 3 hydrogens, further deshielding them relative to the 3 hydrogens that would be there. So those are 2.5, but keep in mind if you have that one, it was between 5 and 6. So that one's the most. Since these are further away from the deshielding effect, they're not as effectively deshielded, so that's why they're only at 2.5. The ability to hydrogen bond results in highly variable chemical shifts for the protons of hydroxyl groups or amines or even amides. And then for carboxylic acid protons, you see that the hydroxyl ones and alcohols range from 2 to 6 and are broad. The amines appear between 1.5 and 4 ppms. They can be broad, and the carboxylic acid proton is going to be between 10 and 11. That's the most deshielded we see. Those will also be broad. These hydrogen bonding protons often exchange with the solvent, meaning their signals will disappear. Thus, these signals are often weak, missing, and or broad. All right, so we have there a whole set of alcohols, hydrogen bonding, seen as a static process, but it's actually dynamic in that they're going back and forth. They're going from one molecule to another. It says this reaction is fast in both directions. So the blue hydrogen, through equilibrium exchange, ends up attached to several different oxygens. So it's going to not show up as much, essentially. The carboxylic acids are between 10 and 11 because the carbonyl group of the carboxyl group, I guess, is going to highly deshield those. You have 2 oxygens near that hydrogen, so they're deshielded more than anything. And again, the amines are between 1 and 4, or 1.5 and 4. And so those are deshielded a little bit, but not as much as the hydroxyl ones. And that would be just due to the difference in electronegativity values of nitrogen versus oxygen. All right, rank hydrogens A through J in terms of their chemical shifts, with 1 being the lowest, 10 is the highest. If a hydrogen appears at a variable chemical shift, like we just discussed with alcohols and such, you can exclude those from the ranking. There are lots of correct answers here, so make your best guess. Well, as I'm looking at it, all right, let's look at the variable ones. We have a carboxyl one. I'll just highlight the whole group. We have an alcohol. And then we've got the amine right there. So those 3 we can exclude. All right. But then we've got these 2, which I would say are the same. We've got that, this. Let me just kind of highlight every hydrogen in as many different colors as I can. Right there. So it's a lighter blue there. All right, so we see all those different colors. And now we're going to rank them. All right, from lowest shift, meaning furthest to the right, to highest shift, furthest to the left. I'm just going to go ahead and say that this is 10, the carboxylic acid. The alcohol, we don't really know. It's 2 variable. Same with that one. All right. Now, looking at the yellow ones, these are alkyl. These are alkyl groups. There's just that. You have this one being vinylic, some classifying these for you. These are also going to be alkyl, but they're alpha to an amine. And I should specify up here, these are also alpha to an hydroxyl group. All right. This one is technically alkyl, but it's going to be alpha to an oxygen plus it's nearish to an alkyne. Then here you have the acetylenic. And finally, this one is technically alkyl and alpha to an amine. All right, so now that we've got them labeled, all right, every alkyl one we have is next to a heteroatom, or alpha to a heteroatom. So comparing those, let's see here, we have the hydroxyl one, we have the alpha to the amine there. We've got the other one over here that's alpha to the amine. So I would say those are going to be near to each other. But then well, you know what? I missed one. This right here is also alpha to an amine. All right, so there's really three of them, actually four. The yellow, the black, the grayish one, the light blue, and the dark green here should all be somewhat near each other. So how do we distinguish them? Well, first of all, this one's going to be the leftmost of those, J. Okay, because it's not J, I. I will be the leftmost out of those four because it's near the hydroxyl group, which is the oxygen is more electronegative than nitrogen. All right, then what I would say is we're looking at those three groups near the hydrogen or near the nitrogen, but excluding that one. Okay. And so there's lots of possibilities here. I would say that the nitrogen, when we look at it, is 1, 2, and 3 bonds away from D, whereas it's only 1 and 2 bonds away from C. So the effect of C is going to be more D-shielded than D. F is also 1 and 2 away. So C and F should be near each other. And you do have an oxygen, I know it's many bonds away right there. You also have the benzene ring many bonds away. So this one should be slightly downfield from C. So when I'm looking at this, again, I see that the yellow one will be the furthest down from those, the I. And then F will be next to its right. And then C. And then D. All right. That's those four. So I've now covered these, that, this, and that, and these. Now we have this one, that one, and that one. We have the acetylenic, which is going to be around 2.5. We have the green one, H, which is bonded next to an oxygen and the acetylenic group, and it's kind of near the benzene ring. So I think H will be very far down left field, or very far downfield. And then B should be even more. Let me actually see if I can move. It won't let me do that. Okay, so let me erase. Let me just scrub over that. We're gonna have B being the furthest downfield of those. So we've got that crossed out. Then I'm gonna do H, because it's so near all three of those, but it's not really directly bonded to them. And then the last one is G. And where does G go? All right, so doing the rest, you have A, we know is 10. So A is going to be, because it's carboxylic acid, the furthest left. Then I would say B is probably next, because that one's the vinylic. And then H. And then we've got, let me see, I'm going to write the letters out. A, B, C, D, E, F, G, H, I, and J. All right, and we've crossed out those, and H. All right, then I have I, F, C, D. And we're excluding J and E. So that leaves F, oh no, I did F right there, and G. So where does G go? G is this one here. Again, it's like around 2.5. You have this thing that's kind of a lot deshielded. You've got all these other ones near the nitrogen, so they're sort of deshielded. And you see the question says there are a lot of correct answers, so you can put it anywhere you want. And it just turns out that that one is actually going to be between C and D, so it's going to be like that. And then we've got 1, 2, 3, 4, 5, 6, 7, 8 of those where we knocked out 2 of them because they're variable. They could be anywhere in between, so you don't have to answer those. All right, next we're going to go into the details of splitting, also known as multiplicity. All right, the splitting or multiplicity of a signal allows us to link the individual signals by illustrating the number of hydrogen neighbors each hydrogen has. The n+1 rule says that a hydrogen with n number of neighbors will appear in the spectrum as an n+1 multiplet. So again, this picture here has the 2 highlighted oranges. Each have 2 neighbor hydrogens, so they should show up as a triplet. M is going to be equal to 2 + 1. This signal has 4 peaks, so you take m-1 to get n, and so that means that would have 3 neighbors. So these hydrogens must have 4 - 1 or 3 neighbors, and you see the 1, 2, and the 3 there. Assume we are looking at the signal of HA with 1 neighbor, HB. HA will be either in the alpha or in the beta spin state. So in other words, it'll be either up or it'll be down. All right, we'll say that's HA. The neighboring atom can also be in either alpha. Let's call this alpha and that beta. In HB can either be up or down as well, alpha and beta. In a sample containing sextillions, quintillions of molecules or atoms with hydrogens in there, there's a chance that the neighboring hydrogen will be aligned with the field while the other one will not be. So really, let's go from A to B, we can have the relationship between the spin states as alpha. We're just saying A is alpha, I guess. And then the B can be alpha as well. or it could be beta. So there's two possible states between those two atoms. If A was beta, B can be alpha, and really these here are the same, that they're opposite. A could be beta and B could be beta, but it turns out like those will be the same as that. So really, boiling it down, we get two possible situations. If A is alpha, B can be either alpha or it could be beta. All right, so we get two different spin states between those two, and that's why it ends up being a doublet. Here we see HA has 3 neighboring hydrogens, and as we should know, that would give us a quartet. Let's see why. All right, if A is going to be, all right, we could have alpha, and then you've got from here, well, actually, wait, this has 3 B's, so we're going to do B1, B2, B3. And B1 could be alpha, B2 could be alpha, B3 could be alpha. B1 can be alpha, and then beta and alpha. We have alpha, beta, beta. Let me draw a line down there. Then we have alpha, we have alpha, beta, beta was the last one. We have alpha, alpha, beta. All right, and then we've got now beta, alpha, alpha, beta, alpha, beta, 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 alpha. Oops, don't want that. We have alpha, beta, beta, beta. There we go. So what we're seeing here is the number of alphas versus betas. We have 3 to 0. We've got 2 to 1, 1 to 2, 2 to 1, 2 to 1, 1 to 2, 1 to 2, and 0 to 3. So it turns out that this is unique, that is unique, because they're all alpha or all beta. But we have these being not unique, but separate, but the same as each other. And then these 3 are also the same. Because the bonds are rotating and stuff, the number of, or the location doesn't really matter, whether it's B1, B2, or B3. It's just the number of them that are beta and the number of them that are alpha that matters. So we have 1, 2, and 3 peaks right there. And 4 right here. Because I had that the same color, it confused me. Should have been a different color. But there's 4 different situations related to what the HA is. And that would be the 4 we see there. So it forms a quartet. And this will be true for all of them. It just always works out that you have an n plus 1 number of peaks depending on the number of neighbors. So every time the magnetic fields of 2 nuclei are aligned, the chemical shift increases by some value we'll call x. When the magnetic fields of 2 nuclei are in opposite directions, the chemical shift will decrease by the same value. In every case, the distance between the peaks of the multiplets is 2x. This value of 2x is defined as the coupling constant and is a measure of the interaction between the magnetic fields of neighboring hydrogens. So this is what this is getting at, is the distance between each of the peaks in a multiplet. A multiplet is anything that has more than one peak within the overall peak. I don't think I need to go into too many details for that. This is like, honestly, stuff that graduate students and above need to really worry about. You guys don't need to, but it turns out that we can have the multiplets split wide or very narrow to each other. The better your NMR, the better you'll see the peaks like this. If it's a very bad one, this might end up just looking like one blob, essentially. The peak heights relate to the probability of the combination of those spin states occurring. For example, if a proton has two neighbors, the spin states can be alpha alpha, alpha beta, beta alpha, beta beta. So there's one combination with two alphas, one combination of two betas, and two combinations that have one each alpha and beta. Draw all of the possible spin states to explain why a hydrogen with four neighbors appears as a quintet, or 5 peaks. I'll let you guys do that on your own because I don't want to do that in the course of this video. How is it possible that a hydrogen can have 4 neighbors? Well, let's just draw a molecule. Let me change the color. All right, let's say we have a hydrogen here, and to have 4 neighbors, you could have 3 over here and 1 over there. So we're looking at that one, and then these could be different things. That's pretty simple. Otherwise, you have 3 and 1. You could have 2 and 2, and that would be how. So again, there's 1, 2, 3, 4. 1, 2, 3, 4. All right, given the molecular formula, C8H8O2, determine the structure that corresponds to the spectrum shown. Let's first find the index of hydrogen deficiency. All right, and that'll be 2 times the number of carbons minus the number of hydrogens minus the number of halogens plus the number of nitrogens, and then plus 2 divided by 2. So we get 2 times 8 minus 0 plus 0 plus 2, all of that divided by 2. We get 16 minus 8 plus 2 over 2 is 10 over 2, which is 5. There's a lot of carbons, but not enough hydrogens. So I'll remind you that double bonds count as 1 hydrogen deficiency, whether it's to an oxygen or not. Rings count as 1, triple bonds count as 2, and so on. All right, so what we see here, we have 5 for the index of hydrogen deficiency, and we got this spectrum. There's an integration of 3, 2, 2, and 1, and those add up to 8, so there's no symmetry in the molecule. Because this is a singlet, there are 0 neighbors. This is a doublet, so 1 neighbor. And we have another doublet for 1 neighbor. And we have another singlet. And so that means 0 neighbors. I guess I haven't really defined neighbors officially, or in a simple way. If we have a molecule and there's a hydrogen here, a neighbor is defined as, actually let me make this the one we're looking at. The simple way of defining it is you have to go 1, 2, and 3 bonds to another hydrogen, and that will be a neighbor. All right, and so 1, 2, 3. It's always 3 bonds away. 3 connecting bonds between hydrogens define neighbors. All right, so now we look at the peaks. We'll look at the shifts last, but we have a singlet, 2 doublets. I should say 2 singlets and 2 doublets for the total of 8 hydrogens. The fact that we have integration of 3 tells me there's going to be a CH3. Now I'll look at its shift. You see it's around, let's say 3.8. A normal alkyl shift is going to be around 0.9. So this is significantly de-shielded, which means that this is probably connected to one of the 2 oxygens, like that. All right. Now what's next? Is it bonded to an ester? Is it this? Is it bonded to something else? I don't know. That's what we got to look at and kind of figure out. But I would say this is a good bet right there. Being that it's deshielded significantly, it's probably bonded to, the carbon is bonded to an oxygen. Then we have these two doublets around 7 and 8, and I'll remind you that between 7 and 8 is an aromatic region. All right, so there's aromaticity here. In a benzene ring, you have 3 double bonds and a ring. So this counts for 4 double bond equivalents, right, in and of itself. And we have 5, based on the index of hydrogen deficiency. So again, all right, maybe we have the methoxy group like this, or maybe we have an ester right there. That would be all of the index, or all of the double bond equivalents, I should say. All right, if we did that, then there would be these hydrogens here. And so we'd have the triplet. Now, this right here has 1 and 2 neighbors, so it would be a triplet. And we don't see any triplets. And so that is not the structure. So, whoops. No to that. So it could be this. We still need another double bond equivalent. And so let's say we have an aldehyde attached to the ring. All right. Now we just kind of make guesses. Where does the aldehyde go? I put it where I put it, and let's see what we get. Well, that one would still have a triplet, which we don't see. If we put the aldehyde here, we have this hydrogen and these. By the way, let's add them up. There's 3 here, 4, 5, 6, 7, 8. So that is like a feasible structure. All right, this one would be a singlet. Hey, and we see a singlet right there, but this would also be a singlet. And that would be a singlet. So this one would have 3 singlets, and we only have 2 in the actual structure. So that's not it either. So now we'll put the aldehyde opposite the methoxy group. And I'll put CH3 here this time. So that'll be a singlet, significantly deshielded to nearly 4. We're going to have this hydrogen as a singlet as well, and that's an aldehyde, so it's going to be like 9 to 10. And we do see that. All right, it's around 10. It's a singlet. And it integrates to 1, whereas that integrated to 3. So far, that's good. Then we've got these 2 being the same, because you could draw a line through the molecule like that. And then you've got these 2 being the same, because again, there's that line through there. So there's 2 different, we have green, red, purple, and yellow, 4 different peaks. We see 4 peaks. If we look at this one, there's only 1 neighbor, so this would be a doublet. And it doesn't matter, like, yes, this one sees that, but they're the same, so they still each only see 1, so they each make a doublet, and they would integrate to 2. And then over here, again, we have another doublet that integrates to 2, which might be that one. Which one is which? Well, I mean, between the two, like, this is the structure of it, by the way, and which one's on the left and which one's on the right. Well, that's that's kind of hard to figure out, but it doesn't really matter because we get the peak we get. I would say that it's probably that. Let's see. I'd say that the ones here will be on the left, and then these purple ones would be the ones on the right. You have the carbonyl there, which is deshielding in that area. Not quite as much as it's deshielding that hydrogen. And yes, there's an oxygen there that's going to pull through induction away from these two hydrogens. But you have the carbonyl deshielding. You have the fact that this is going to pull, it's an electron withdrawing group. It's also going to pull through induction. And so you have them close to each other, but I would predict it to be like that. When two neighbors of the same hydrogen atom are in different chemical environments, the splitting patterns are often not clean. This is because the coupling constants are not the same. So the molecule we're going to use here as an example is this, which is trans-butanoic acid. All right. If we were to look at the molecule, and specifically at HB, all right, ignore this stuff over there. It has the neighbors HA and the neighbor HC. There's two different neighbors, and they're in different chemical environments. HC is vinylic, and it's alpha to a carboxyl group, and HA is allylic and are alkyl in nature. So the way B experiences A and experiences C do slightly differ. If we were to consider what HBCs with just HA, if, let's say that didn't exist, then HB would be a quartet, and the coupling constants would be 7 hertz. That would be the JA to B. I already have that there. If we did the other thing where we got rid of HA and kept, and we only looked at HC, which I know it's hidden right now, but this would make a doublet. And the coupling constant there for B to C would be 15 hertz. Now, when we look at the picture, this is a sextet. But normally, if we drew a sextet, we would have 2 big peaks in the middle, followed by 2 intermediate peaks in the middle-ish, to the side of them, and then 2 small peaks out of them. But this one is small, and then 4 in the middle that are the same, and then small. So it's not quite a normal sextet, all right? It's not a quartet, and it's not a doublet either. So there's weird mixings going on. Okay, so we're going to do what's called a splitting tree from here. We're going to take the information starting with this doublet here. So we're going to have HB, and we're going to start with a doublet. And we're going to go down from there. Now I'm going to put a ruler up here. I don't know if you'll be able to see it, but these are going to be split by 15 hertz. So that means 7.5 on either side of this line. 1, 2, 3, 4, 5, 6, 7.5. And 1, 2, 3, 4, 5, 6, 7.5. All right, so now that's just like a guiding point for me. These are split by 15 hertz. That's the JBC, which is about 15 hertz for their splitting. I'm going to do the same for each of the other two. We're going now the JA to B. All right, so now these are going to be split by 7 hertz each. And the JA to B is going to be a quartet. All right, so we have 1, 2, 3.5, 2, 3, 4, 5, 6, 7, 7. All right, so let me get rid of those. Again, those are the guiding points. We have lines here, here, there, and there. That's one splitting. And then the next one, again, bring that over. Right around there. All right, so now we have a line here, we have a line there, here and there. And so you see 8 peaks. So, hey, why isn't this an octet? And we see the real thing right there, there's 6. Well, it turns out that the difference, let's go straight down from here to there, is 3.5 hertz. And the same could be said for this, is 3.5. And from here to there is 7, and from here to there is 7. So there's a little bit of a gap. Those gaps end up being 1 hertz in between, and so you add it all up, you get the 15 hertz. Well, it turns out that these are so close together that for many NMRs, they'll just end up looking like one peak. So you get 1, 2, 3, 4, 5, and 6 peaks. And hence, it looks like a sextet like that. Now notice the thickness of these are a little wider than out here, but the height is the same. And so that's kind of telling you something, but that's what it would look like. Now, the bottom part here is using a molecule of like butane. And so it doesn't really match up with the rest of it. So we're just going to focus on that right there. This is for diastereotopic hydrogens. When 2 hydrogens are diastereomeric, they give different signals in the NMR. Now, looking at the structure of oxazolidinone here, you'd think that HA and HB might be the same, but keep in mind HA is below the ring and near this benzene ring, whereas HB is above this ring, I should say, and is nearer to the HC. And we can see that in this picture here. I know it's blurry, but sorry about that. It does say replace the hydrogens with deuteriums, HA or HB, and you get those are clearly diastereomers. If you can do that and you make diastereomeric hydrogens, that means the spatial arrangement of the things are different. And again, HA is below the oxazolidinone ring near the benzene ring, and HB is above it near the HC. So they're going to give different signals. So HA is being coupled to HB and HC as well as HB is. So they give different signals. HA is a doublet of doublets, and so is HB a doublet of doublets. Since HA is near the benzene ring, it's going to be significantly deshielded. Since HB is not, it's definitely not as deshielded. It's more shielded. And HC is in the middle. That one's a triplet because it's coupling to both HB and HA, so it's got 2 neighbors, therefore it's a triplet. Let's try it. Replace HA, HB, and HC in methylbenzene with deuterium. What is the relationship between the 3 products you obtain? Based on this, how many signals would you expect for these hydrogens in the proton NMR spectrum? Well, the reality is, it doesn't matter which one we change. Let's say I change HA to a deuterium. This bond can rotate and put it in the place of where HB currently is, or it could be where HC is. So all 3 of those are the same, therefore you only get one option, and therefore you get 1 peak for these 3. They're not going to split into weird coupling things. Now, so far, all of this dealt with proton NMR. There's also carbon NMR and phosphorus and fluorine stuff, as mentioned earlier briefly. We will only ever use hydrogen proton NMR spectroscopy in our labs. Other labs will often use carbon NMR, carbon-13 NMRs. Very rarely will people use fluorine or phosphorus, but it's not unheard of, obviously. So most common is hydrogen, then carbon, then the other two. Carbon-13 NMR is also a useful technique for structure identification. It allows us to identify functional groups that don't contain hydrogens, i.e. carbonyls or internal alkynes, along with carbon atoms with no hydrogens, like a quaternary carbon. The background theory for carbon-13 NMR is covered in less detail than it was for proton NMR because much of it is based on the same principles. The difference: whereas almost every hydrogen is NMR active, only 1% of carbon atoms will be able to be detected using NMR. And that's because hydrogen, it's like 99% of the atoms of hydrogen are hydrogen 1 and therefore are active readily in NMR spectroscopy, whereas for carbon, the carbon-13 isotope is only about 1% of the atoms of carbon. The rest is carbon-12, but because carbon-12 has an even number of nucleons, I should say, because it has an even number of protons and neutrons, it's not NMR active. The spectral width in carbon-13 NMR runs from 0 to 250 ppms. You can imagine that the carbon weighs more than a hydrogen, so causing it to flip requires a higher frequency. Integrals do not give the number of carbons giving rise to a signal. In carbon-13 NMR, we only know the number of unique carbon environments. Splitting. There's only a 1 in 10,000th chance that a carbon-13 nuclei is a neighbor to another carbon-13 nuclei, and thus carbon atoms are not split by other carbon atoms. Most carbon spectra are obtained in proton decoupled mode. Analyzing a carbon-13 NMR spectrum is greatly simplified compared to an NMR or proton NMR spectrum. The only information given in a standard carbon-13 spectrum is the number of sets of equivalent carbons and where they appear in proximity to certain functional groups. So we see in methylcyclopentane, we have only 4 signals because the carbons here and there are the same, and the carbons D, those two Ds are the same, and then you've got B and A as different ones. Now the hydrogens would be the same, but they're split. There'd be 4 hydrogen environments as well, but they'd have their splitting patterns, and carbons don't, so it's a lot easier to see where they are. I mean, you do miss out on the number of carbons because it can't be integrated and you're missing splitting, but at least you know how many different environments there are. So you take together proton NMR, carbon NMR, and that can really help you build the puzzle to what the structure is. If it's not enough, you might use an IR. They'll tell you the functional groups for sure, whether it's an ester, carboxylic acid, or whatever. And then you could use mass spec to break them into chunks, and that still helps you figure out functional groups and pieces of a molecule. You see in this second molecule, there's 6 signals of carbons, A, B, C, D, E, F, A, B, C, D, E, and F. And then we have over here 5. These are the same. These are the same due to symmetry. These are the same. And then C and E are different because C is closer to these methyl groups, whereas E is not. And we've got 9 signals in this molecule. All right, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Pretty straightforward. All right, so a molecule like this has 1, 2, 3, 4, 5 peaks. And if we look at the other peak or other NMR, you see there's 1, 2, 3, and 4 different peaks, and they show up A, B, C, and D in the NMR spectrum there. How many signals would you expect in the molecules shown here? Well, although there's 2 methyl groups, one is on an alkene and one is not. So those are definitely different. So there's going to be 1, there's going to be 2, 3 and 4, 5 and 6, 7 and 8. Over here, though, we have 3 methyl groups. This molecule is symmetrical at this, through the center of it. Those 3 methyl groups are going to be the same ultimately. These carbons will be the same. And then these 3 will be the same. So that one would have only 3 peaks. So we can see a general trend or idea of where certain functional groups show up in carbon-13 NMR spectra. So we see the carbonyl is going to be around 200, or really it's like 160 to 210. Alkenes are from 100 to 150. Aromatic carbons from like 110 to 150, maybe 120 to 150. Alkynes from, 80 to 90, around there. Alcohols and ethers from like, let's say 45 to 90. The alkyl halides from like 30 to 60 or so, and alkanes from 0 to 40. Structures are usually determined with a combination of spectral measurements. So here we have a molecular formula of C6H14O. Let's do the index of hydrogen deficiency. It gives us 0 though there, but 6 times 2 minus 14 minus 0 halogens plus 0 nitrogens plus 2 over 2. So we get 12 minus 14 plus 2 is 0. So that does match. There's no double bonds and there are no rings. So this is a saturated hydrocarbon. That means because you have an oxygen, it's either an ether or an alcohol. All right. We have 6 carbons and it says 2 peaks for 6 carbons. That means there's going to be symmetry. Obviously, that one's going to be where the oxygen is bonded to, and this one will not. I would look at that, knowing its formula, and say, this, well, let's say, is it an ether? If it was, then you'd have 1, 2, and 3 peaks, because you'd have the same on the other side of it. But this only has 2. So we'll move on to the over here to the proton spectrum. Again, only 2 peaks. We have an integration of 6 and an integration of 1. And again, there's supposed to be 14 hydrogens. So really, this should be 12 and that should be 2. A doublet and a septet. A doublet means there's 1 neighbor, and a septet means there are 6 neighbors. Well, if there's 6 neighbors, that means there's a CH3 and a CH3. And that would be this right here. If these are the same, they would see that hydrogen as a doublet. Now, that's 3 carbons. Now maybe this still is an ether and I had just thought of it the wrong way. Now, if I were to draw this like that, you'd see that the hydrogen's sticking off here and there. This molecule is symmetrical, right? So in this case, these 2 are the same. These 2 are the same. But even, I could say these 2 are the same and those 2 are the same. So really all 4 of them are the same. You're getting 1 peak from those, and you're getting this 1 peak right here in the carbon NMR. But also we matched up to the proton NMR. Now, I don't even need the IR. And that's the value of NMR spectroscopy, is sometimes we don't even need this. We see here, there's no band at 3,300 centimeters. It's not broad, so it's not an alcohol. You could know that easily and just go straight to the ethers. There's a CO stretching bond, so it must be an ether, as we see at about 1,100 to 1,200. All right, the mass spec, you have the M equals M plus is 43 there. That's these fragments. You got 12 plus 3, 12 plus 3, 12 plus 1. So 12 plus 3 is 15, times 2 is 30, plus 12 is 42, plus 1 is 43. So you'll notice you've got that peak. You've got a peak at 45 as well. I don't know where that comes from, but the 43, I don't know, like the mass spec is much more complicated. You have all the way up to there, which is like nearly 90. It turns out it's probably 87, which is 15 less than 102, which is what its molecular weight is. So it's probably a methyl group that's been kicked off. So there's, it might be a peak there as the whole thing that's just lost an electron. Then you get this and whatever. You can figure all that out. But we did it without the mass spec, without even the IR. We figured out that wasn't it. It's not an alcohol, but it's diisopropyl ether. And so that's how we read nuclear magnetic resonance spectroscopy. We're not going to go into phosphorus or fluorine spectra. If you needed to, you'll learn those later. And there's other stuff in the book that I'm not going to go into because it's too complicated, or it's just too much. It's more than you need. But, long story short for this whole chapter, this same principle is used in magnetic resonance imaging at hospitals. And so if you've listened this far, here, great, thank you. But hospitals don't use hydrogen atoms to do it. They use entire water molecules. And the water molecules will flip back with or against the magnetic field that a human or some other animal is being placed into the MRI machine. But the big tube is really just coils of copper wire around you, creating the magnetic field. They turn it on. Magnetic field forces the water molecules to line with it or against it, and then they irradiate you with radio waves. And those either, cause the molecules to flip their spin, or it doesn't. If it causes it to flip, it's going to create a signal as it relaxes back down and emits radio waves back, and then you have the detector detecting that change in energy ultimately. And it does it, in 3 dimensions, so it can figure out where the water is ultimately, and that's how you get the signals, because it's measuring it at in slices throughout your body essentially. And so it can do it in flat, but it does it in slices, and so you get an MRI. And it's not really looking at your organs per se, it's looking at water, but the density of the water, the concentration of it or whatever, cause the differences in those signals. So again, I know it's not mentioned in this chapter at all, but that's how MRIs work, and it's the same principle as this. We're able to figure out organic, and by that I mean like organs of a body, your organic spectral imaging in such a macro scale, and I find that amazing. And we can do it at such an incredible nanoscale, the size of atoms. We can figure this out, which is also incredible. So this principle is really great. Anyways, that's it for chapter 15, and we'll move on now to chapter 21.